Hello everyone and welcome to a new lesson of the Algo one-on-one chapter. As the title suggests, we are going to talk about sorting. First of all, we should know what is sorting, why do I need sorting, and then we will see a couple of sorting algorithms. In this lesson, we are going to talk about the most fundamental sorting algorithm, which is selection sort. So let's start. What is sorting? Sorting is a process of arranging items systematically in a sequence ordered by some criterion. Some fundamental criterions are numerical order, and that is when we want to sort a collection of numbers, lexicographical order when we want to sort a collection of strings, by abscissa, then by ordinate when we want to sort a collection of two-dimensional points. And in a lot of problems, we are going to define our custom criterions. To demonstrate the numerical order criterion, let's say for example that we have this list of numbers. The increasingly sorted list will look like this. So as you can see, every number is greater than or equal to the previous one. The decreasingly sorted list will look like this, and of course, it will be the reverse of the previous list. To demonstrate the lexicographical order criterion, let's say we have this list of strings. The increasingly sorted list in lexicographical order is this one. For the by abscissa, then by ordinate, let's take this list of points. Each one is determined by two numbers, which is the x-coordinate or the abscissa and the y-coordinate or the ordinate. And this is how the increasingly sorted list will look like. As you can see, every element has the abscissa and the ordinate greater than or equal than the one of the previous point. Now let's define our own criterion. Let's say the criterion is the absolute difference between the abscissa and the ordinate. So it's still a scenario for two-dimensional points. Let's say the list of points is the same one. Then the increasingly sorted list will look like this. As you can notice, it's way different than the previous one. And this is because this criterion is much different than the previous one. In this increasingly sorted list, the absolute difference between the abscissa and the ordinate of some point is greater than or equal to the absolute difference of these coordinates of the previous point. Alright, I think we now understand what is sorting. So the next question is, why do I need sorting? There are two main reasons for sorting a collection of objects. The first one is proximity. In a lot of problems, we are going to need to be able to support fast access to similar objects. One example that I can think of right now is having a list of numbers where we want to have the equal elements one after another. The second main reason for sorting a collection of objects is fast searching. If you remember the previous lesson, in order to binary search an element in a collection, we needed to have that collection sorted. These are the two main reasons that you should remember, but don't worry, we will learn more about them during problem solving. Now let's learn more about sorting algorithms, and for that we will start with one of the most fundamental and simplest of all of them, which is selection sort. Selection sort operates by a simple principle, and that is, we have a pointer, and let's call it I, which goes from 0 all the way to n-1, where n is the number of elements in the array. And at each moment of time, we know for sure that the smallest I elements from the whole array are sorted and placed on the first I positions. As you can see in this example, where I equals 3, indeed, the smallest 3 elements for nums are placed on the first 3 positions in the increasing order, 1, 3, and 5. The other elements are placed on the other positions and they are not necessarily sorted. Now, in order to increment the pointer I, we need to make sure that the smallest I plus 1 elements from the array are sorted and placed on the first I plus 1 positions. The only element that might not be right is the one on position I. And one thing we know for sure is that this element is not going to be found on the left of position I, but it's going to be equal to the minimum element from the subarray nums of I and n-1. What is the minimum in this example? That's right, It is 6. Now this minimum element needs to be placed on position I, and the element that was previously there now needs to be placed in the unsorted subarray starting at position I plus 1. So what we can do in order to achieve this is just swap nums of I with nums of j. And here we go. Now the right value is placed on position I, so we can increment I and continue the algorithm. And this is exactly what we will do for each pointer I, starting from I equals 0, because we suppose that no element is placed on the right position. And we will end the algorithm when I equals n-1, and that is when the whole array is sorted. Now let's take an example array and apply the whole algorithm to understand better how it works. We start with I equals 0, and now we have to find the minimum from the subarray nums of 1 and 7. Now one way to do this is to have a variable which stores the position of that minimum element and iterate through all the elements and update that variable. But let me give you one trick. For a cleaner implementation, we can store the minimum found so far directly in nums of I. So let's take another pointer j that will start from position I plus 1, which is in our case 1, and always check if nums of j is smaller than the current nums of I, then we can swap them. Here, nums of j is less than nums of I, so we can swap them and increment j. 9 is not less than 3, nor is 7, nor is 6, but 1 is. So let's swap nums of 0 with nums of 5 and increment j. Nums of 6 is not smaller than 1, nor is nums of 7, so here we finish the second loop. We have found the smallest element in the array, which is 1, so now we can move to I equals 1. J will start from I plus 1, which is 2, but nums of 2 is not smaller than nums of 1, nor is nums of 3, nor is nums of 4, but nums of 5 is. So we will swap nums of 1 with nums of 5. We continue looking, but nums of 6 is not smaller than the current nums of 1, nor is nums of 7. So here we finish the second loop, and we can say that we have found the second smallest element, which is 3. So now we jump to I equals 2. J starts from 3, nums of 3 is less than nums of 2, so let's swap these two. Increment j, nums of 4 is less than nums of 2, so let's also swap these two. Increment j, again, nums of 5 is less than nums of 2, so let's swap these two. And after this last swap, nums of 6 and nums of 7 are not less than nums of 2, so here we stop. We have found the third smallest element, and we can jump to I equals 3. J equals 4, 7 is less than 9, so let's swap them and increment j. 6 is less than 7, so let's swap them and increment j. And from the other two elements left, none of them is less than nums of I. So we have also found the fourth smallest element, and we can jump to I equals 4. And we continue doing the same for every I from 4 to 7, and in the end we will have the array sorted. Now let's see a little bit how the implementation looks like. For each I between 0 and n-2, for each j from I plus 1 to n-1, if nums of I is greater than nums of j, then we just swap nums of I and nums of j. And this is it. At the end of the algorithm, we will have the array nums sorted. Now what do you think is the time complexity of this algorithm? Because the comparison and the swapping are both constant operations, we can consider them as big above 1. And because our two nested for loops make a total of almost n squared iterations, the time complexity of this algorithm is big O of n squared.